over n, which of course goes to 0. So this is really similar to a random walk, right? And sure, this new Markov chain converges to the absolute value of Brownian motion, but its local time goes to 0, even if you didn't scale it. So just by doing some very simple local modifications, you can destroy the local time convergence. So let me go to a more stable situation, and those are the results of Borodin from 1984. Now consider the same recurrent random walk on the integers of span 1, but now assume that it's on the domain of attraction of a stable process of index alpha between 1 and 2. So you could have any index between 0 and 2. Here we're excluding indices from 0 to 1 because otherwise the limiting process does not keep on coming back to 0. So let L1 be the local time at 0, this counting process local time of your random walk. And well, you know that the random walk can be scaled to converge to this stable Levy process X. So you consider the local time at 0 of your stable process X. And here it's again important that alpha belongs to 1 or 2, because otherwise local time is just 0. Then you can find scaling sequences A and Bn, An and Bn, such that if you scale your random walk like this, so scale time by a factor of n and space by a factor of An, and your local time, it will also have time scaled by a factor of n, but now the space will be scaled by a factor of Bn, and this An of B and Bn have some relationships that we could state, but chose not to. Then you have that the scaled random walk and the scaled local time converge in probability, again, or in law, towards your Levy process X and its local time. So again, this is a result that we'd like to understand in a more general situation. So here's a picture of these random walks, which are in the domain of attraction of a stable process. And you can see now that they feature both jumps, rather large jumps of both signs, both upwards and downwards. And this is a picture of its local time. So you can note that even if we used 1,000 steps and the random walk already looks very much like a stable process, the local time really doesn't look yet like the kinds of functions that have been plotted. So that reflects this Bn so we should take an even larger n to get a nice picture of the local time. Good. So why are we interested in these local time processes? Perhaps the last talk gave us some motivation for why we would want to get local times. Here's a different type of motivation. So I really like these models of random trees, like this one here. And one of the reasons is that they can be studied thanks to their relations to random walks. So this is a picture of a Galton-Watson tree, which has a picture of a Galton-Watson tree. And here are the generation sizes. So this is one individual which has 3 descendants here, and that's how you get all successive generations. And the particular feature of Galton-Watson trees is that their generation sizes are a Galton-Watson process. So what people have been doing since the 90s is to try to study the limiting aspects of these trees when they're conditioned to be large. And one way to do that is through what's called the height process of this random tree. And it turns out that the height process can be related to the local times of a random walk. How? Well, there is a random walk that's underlying this tree. I'm not going to describe how to construct this random walk. But the point is that this height process that is so important to get convergence of random trees is basically the local time of this time reversed random walk reflected under its maximum. And when you do that reflection, you're talking about the local time at zero. So I'm going to have some pictures about that afterwards. And I was planning to do a picture here, but couldn't for technical reasons. And that's the point. So this height process is basically the local time of a reflected backwards random walk. And so we want limit theorems for that. Good. So let me talk about the local time that we'll be using and about the setup that we'll be considering. And that is the setup of regenerative processes. So a process X is regenerative at some state X so here's a graph of your process X, and for every T, you're going to define the first visit to the state X after time T. So that's this dt that's plotted over here. And if when you shift your process to start at this dt, so you consider the process X of dt plus whatever argument, and you condition it on all the trajectory up to dt, then that has the same conditional law as X. If that happens for every T, you say that your process is regenerative at X. So what's an example of a regenerative process? You take any strong Markov process, and then it's automatically regenerative at any state thanks to the strong Markov property. So for any regenerative process, there exists a regenerative local time, which is this unique process that increases only when X visits X, and such that its increments are going to be independent of what the process did beforehand and have the same law as the original process. So that's definition of regenerative local time. And what's important here is inverse local time. Why? Because inverse local time is a subordinator, which is of course now characterized by its Laplace exponent, which can be written in this way thanks to the Levi-Khinchin formula. And let me just point out a difference between the usual Levi-Khinchin formula, and it is that we allow for infinite jumps, which means that you did an infinite excursion outside your regenerative state. So for example, if you have a transient strong Markov process, then at some point you stop visiting your regenerative state, and then you have an infinite excursion, which gives you an infinite jump for the subordinator. So in other words, you can consider also tailed subordinators. So let me describe first the main limit theorem and then some applications. So the main limit theorem, I'll describe first the setting and then the results. So we're going to assume that we have a process in continuous time that is regenerative at some state at which it starts. We're going to assume that X is regular and instantaneous. What does that mean? It means that, well, you start at X and you immediately go out of X, and also you immediately come back to X, meaning that for every epsilon greater than 0, there exists 2 times, say, S epsilon and T epsilon, such that at S epsilon, you're away from X, but at T epsilon, you're at X, right? And what that means is that this random set of times at which you visit X is perfect and totally disconnected. Good. So again, we define L to be the local time at X, tau to be its inverse local time, and mu is going to be the Levi measure of the subordinator tau. So it's what appears here in the Levi-Khinchin formula. Good. So that's the setup in continuous time. So let me describe the setup in discrete time. So in discrete time, we're going to assume that we have a sequence of discrete time regenerative processes time takes place in natural numbers divided by n, which starts also at this x, and it, of course, regenerative at x. We define the natural counting process local time, which is just the number of visits that you do to the state x. And we're going to do something. We're going to introduce mu n to be the law, the common law of the excursion lengths of this xn. Then we're going to define the endpoints of the excursions away from x in the following manner. So you fix any t, either in discrete time or in continuous time. So here's your t, and here's the graph of your process. And you define the first visit to x that you do after time t, and the last visit you do to x before time t. Those are your gt and dt, and you can do that actually also for the discrete time process. So with this setting in mind, we have the following theorem. We're going to need to normalize the local time, and the way to get the normalization constants will be through the Levy measure of your subordinator tau, and with the common law for the excursion lengths of your regenerative process. So you fix any L that's not an atom of this measure mu, and then you define the sequence AN, and that's going to be your normalization constant. The theorem says that if your discrete time regenerative processes converge to the continuous time regenerative process in probability, and your excursion endpoints also converge in probability, then the pair consisting of your discrete time regenerative process with its scaled discrete local time converges in probability to your limiting regenerative process plus its local time. So this is, in a sense, a generalization of all these theorems that I gave you before of Borodin and of Perkins. And so what I'll do next is to describe some more applications of this. First, let me just tell you that this theorem changes the difficult problem of proving convergence to local time to the problem of proving convergence of these endpoints of excursions. And we have two ways to achieve that, to prove in examples that the conditions of the theorem is satisfied. One of them is a pathwise approach, and the pathwise approach is always simpler. The second way we have to prove that we can apply the theorem is when it's in a more distributional setting, and that's usually a lot more technical. So typically the proofs that the conditions of our theorem are satisfied in the pathwise approach take basically half a page, whereas it can be, at least 5 pages for all these other distributional applications. So let me give you first a pathwise application, so a simple one. Consider now a sequence of skip-free random walks, such that when you accelerate time, they converge weakly towards any totally asymmetric Levy process X. You'll notice here that we're not scaling space, only time. And that's because we're considering already a sequence of random walks. So the spatial scaling can be introduced in the sequence, right? And good, so what's a skip-free random walk? It's a random walk on the integers or on some integers over some Bn, which can, for example, jump downwards just by 1, but upwards by any amount. So when you take the scaling limit, your limiting process will only feature positive jumps. So that's a skip-free random walk and a totally asymmetric Levy process. You're going to assume that your limiting process is of infinite variation so that you can define a non-trivial local time. Then you just prove that 0 is regular and instantaneous, and that if L is any version of the local time of x at 0, and Ln is our natural counting process local time of xn, then we can, well, this local time invariance principle can be applied on an adequate probability space, and there exists scaling constants an such that the spatial scaling for the local time is now an, and together with the skip-free random walk, it converges to x and L. So again, this generalizes Borodin's and Perkins results from either the finite variance setting or the stable domain of attraction setting into a general Levy process setting. The price we have to pay for this simple applications is that we can only consider skip-free walks, right? So we're less general in that, but otherwise, to prove that the conditions of the past theorem hold is really a very simple thing. So this is our first application. Second application is as general as one could hope for. So we're going to assume that we have a regenerative process, which is quasi-left continuous. Don't worry too much about that. I'll explain in a minute why you don't need to worry. And that it actually satisfies this stochastic differential equation, which is driven by a stable process, which only features positive jumps and is of infinite variation. So of index between 1 and 2, as before. So typically, when you have solutions to this stochastic differential equations, if you put conditions of adequate conditions on F and B, your solution is actually a Feller process. So you don't need to worry about being regenerative or quasi-left continuous. So what are the conditions that we're going to need on top of that from F and B? We're going to assume that F is non-negative, that at the state Z at which you started, F is not 0, and just to simplify the proof, that your drift is bounded in a neighborhood of the point at which you chose to start. Then you can prove that Z is regular and instantaneous, and that for any sequence of discrete time, discrete space, regenerative processes Zn, whose time runs on natural numbers over n, and which takes value on a scaled integer lattice, which contains scaled and shifted, so that it also contains this Z, which are also regenerative, which are skip-free to one side, and which converge in probability to Z, the local time invariance principle can be applied, and you can construct the scaling constants such that your approximating process with its scaled local time converges to your solution, sorry, here it should say X, to this stochastic differential equation, and its local time at 0. And this is regenerative local time. So I do think that this shows that the conditions of our theorem are such that you can prove them in quite general circumstances. I think this is the first result that shows you that convergence of local time should be expected. Why? Well, for example, X could be a Brownian motion, and then Z is just a diffusion, right? And this is saying that no matter how you approximate your diffusion by skip-free to one side processes, the local times just converge, right? But this is telling you a lot more. You can also do that in the stable setting. Good. And actually, you can go beyond that, the stable setting. But to do that, and to use the pathwise methods, which are so simple, again, half a page proves that we're in the setting of the main theorem. to use this pathwise techniques, it is convenient not to consider this stochastic differential equation, but actually a time change equation. So the reason we chose here a stable process is so that we could apply a theorem of Kallenberg to change this stochastic differential equation into a time change equation. So so you can, with another stable process X, which I wrote with the same letter, sorry about that, it could have a tilde. You could see that a solution to this stochastic differential equation actually can be written in this way. Z of t is equal to initial value plus your stable process at an integral of the function f, absolute value to the power alpha, applied to z, you integrate that, plus, of course, the drift part. And the reason we prefer this second way of writing is because it allows us immediately to transfer path properties of the stable process into those of Z. So it is thanks to this representation that it is trivial to prove that states are instantaneous and regular. Good. So this is how we prove the theorem. And once you do that, you realize that you no longer need a stable process here. You can actually put any spectrally positive Lévy process of infinite variation, and you could add in an independent subordinator for free. Same theorem holds. So why do I prefer this other way of writing? This connects also to the last talk. When your process X is a stable process, say of index alpha, and your process Y is a subordinator, an independent subordinator of index alpha minus 1, and you take B equal to 0, then this process here is one of these stable versions of the CIR model introduced in the last talk. So this is why we prefer this way of writing. So again, in the setting of CIR processes, we can just show that local times converge. No matter how you approximate your CIR process or your alpha CIR process, which now features jumps. Now we come to more complicated applications, and that would be to local times at 0 for random walks, which are now in the domain of attraction of a stable process, but which can feature jumps of both signs. So they're no longer spectrally positive. Spectrally positive is very good for this pathwise applications, but we wanted also to see if we could recover some of these results of Borodin and Perkin. So we take a random walk whose jump distribution has span 1. X is going to be a stable process of index alpha between 1 and 2. Assumptions is that we can scale the random walk to converge to this stable Lévy process. And then we can apply our theorem. But here, things get very tricky. What we need to do is first, we only assume convergence in distribution of this xn to the limiting Lévy process x. So first we place ourselves in a probability space where the convergence is almost sure. So we can do that thanks to Skorhod's representation of weak convergence. Then we prove that in that same probability space, the endpoints of excursions straddling deterministic times converge also either in probability or almost surely. And then we can deduce the convergence of the local times in probability in that probability space. And that's how we get the results. So I wanted to talk a little bit about the technique that we need to do to get that result. And it basically has to do with, so you have your stable process over there. And what you need to prove is that the heating time of 0 after any time t converges, if this is for xn, that t0 of xn converges in distribution of xn, if you want, after time t, converges in distribution to the heating time of 0 of your limiting Levy process. And that is a hard problem for random walks. It's a little bit what Borodin had to do to prove his limit theorem. And usually when we have to deal with this distributional applications of our main theorems, we always have to worry about convergence of heating times of points, which is not trivial. So that's what complicates the application of our main theorem in distributional settings where you have jumps of both signs. So this application has to do with the random trees that I talked about very briefly. So we're going to consider a Levy process X, and we're going to define the reflected process R given by R of t equal to X of t minus underline X t, or X underline t, where X underline t is the minimum of X on the whole interval 0 t. So here's a picture of what we're doing. So this is Brownian motion, and we're seeing it from its cumulative minimum. Here is the cumulative minimum process. So you can see here the excursions above the cumulative minimum. We draw them again, and now we do the difference to get these excursions to start and end at 0. So this is the reflected process, and this can be considered not only for Brownian motion, but for any Levy process, and it turns out to be a Markov process, a Fettler process on top, so regenerative at 0. So it has a local time. So what are we going to do? We're going to consider the same construction, but made out for random walks. So you consider random walks jumping at times 1 over n, 2 over n, etc. Define their cumulative minimum, the running minimum, as well as the reflected process for the random walk. Then there's this more recent theorem of Chaumont-Doni, which was motivated by the random trees, by trying to prove convergence of random trees, which says that there exists this scaling sequence Bn such that, okay, so that's the assumption, sorry. So that you can scale your nth random walk by Bn so that it converges to your limiting Levy process. For the limiting Levy process, you need to assume that 0 is regular for the half-line minus infinity 0, meaning that you immediately visit some negative value when you start looking at the trajectory of your Levy process X. Then you can prove that 0 is regular also for the reflected process, and that therefore you can consider its local time at 0. And furthermore, that your reflected process scaled by the same scaling as for the random walk, together with its scaled local time. I didn't give the explicit expression for the scaling constants because it's quite complicated in this theorem of Chaumont-Doni, converges to the reflected Levy process together with its local time. So we can obtain this theorem this exact theorem by applying our main result. And again, this falls into the framework of pathwise applications of the result, so that it's a half-page proof to get this result of Chaumont and Donny. So these are 4 different applications that I wanted to present, and there's a fifth one that we're working on, but we're not done with all the details. So let me turn to that one. And it's still, part of it is still conjectural. And that's to consider local times for Galton-Watson processes with immigration. Again, I'm very interested in limit theorems for Galton-Watson processes with immigration because their scaling limits are exactly, well, they're called continuous state branching processes with immigration, but they generalize, again, this CIR model and this alpha CIR model that was introduced in last talk. So what is this? Let me just be very clear on what we're doing. So consider any reproduction and immigration mechanisms. So those are just 2 probability distribution on the positive on the non-negative integers. You take psi in and eta n to be 2 independent IID sequences with respective laws F and G, and you construct, as usual, your Galton-Watson process with immigration by starting at K, and just for the sake of concreteness, think that K is equal to 0, and but letting Zn plus 1 to be the sum of the chi's In from 1 to Zn, plus the immigration component. So this would be the Galton-Watson part, and the immigration component would be these etas. You just sum whatever immigrants arrived in generation n plus 1. So here's a picture of your whole genealogical forest for the population. But what we're really interested in when we do this construction is in the generation sizes. So meaning the number of initial individuals, which could be 1 or 0 or k or whatever. And then the number of individuals which comprise the successive generations. And notice that there are some light gray and dark gray boxes. The dark gray boxes signal the arrival of immigrants. So this is the discrete model that we'll consider. Here's just a larger, so we consider time here. I think it's probably up to 100. And the reason I put this picture is so that you can see that a kind of scaling limit starts to emerge, right? And what's interesting about this process is when you tune your parameters correctly, your population will die out. And it will have to be restarted through immigrants, right? So 0 will be recurrent when you tune your parameters adequately. Good. So there's a second construction of the Galton-Watson process with immigration, which is a lot less, I think, known. And that is a time change construction. If you start with C0 equal to 0, Z0 equal to K, and you define Zn plus 1 to be K plus X at Cn plus Y of n, and now you increase C of n by letting Cn plus 1 be equal to C of n plus Z of n, then you can prove that this is just a construction of your Galton-Watson process with immigration, where X and Y are just independent random walks with jump distributions F tilde and G, where F tilde is just a shift of F, right? So I think this is a very nice exercise for students to train them on their use of the strong Markov property and to introduce them to time change equations. And the point is that in these types of equations, it is basically not too hard to pass to the limit. So if you now choose your jump distributions f tilde and g depending on n, so that your xn and your yn converge to Lévy processes, and you define z of n as the solution to this equation, then you can prove convergence to what would be the limiting equation, which is just a continuous time version of this recursion that we put up here. Now, what are the assumptions that you need to put? Well, this is a large population limit, so you're going to assume that the number of initial individuals divided by n goes to some z, which can actually be equal to 0. And you're going to assume that there's, in a sense, a balanced scaling between the reproduction and the immigration. So for the reproduction, you're going to scale time by a factor of n times bn, and space by a factor of 1 over n. Whereas for the immigration, space will have the same spatial scaling, but now the temporal scaling will be bn instead of n times bn. This is the correct balance assumption in order to get that your sequence of Galton-Watson type processes with immigration converge to what is called a continuous state branching process with immigration. And the branching mechanism is now the Laplace exponent of x. The immigration mechanism is now the Laplace exponent of y. And your process satisfies this time change equation. Good. So this is the setting within which we think that we can apply our main theorem on convergence of local times. We believe that under this assumption on the limiting process, we can use our main theorem. So far, we're not yet here. And I won't even get into the details of explaining why this is a relevant assumption. It has to do with 0 being regular and instantaneous for this CBI process. But there's a very particular case that we can do, and that's the CIR, or squared Bessel case. And that's when your Galton-Watson process, so you're going to start with only one Galton-Watson process, which you're going to scale. It has a geometric 1/2 offspring distribution to make it critical. And the immigration is going to be geometric of parameter P. You're going to define this parameter delta to be equal to 1 minus P over P, and you're going to assume that that belongs to 0, 1. Now, you scale your Galton-Watson process with immigration, scale, so time and space, both by a factor of n, and define ln to be its local time at 0. So that's for the discrete setting. For the continuous setting, you define z to be, well, we already introduced the time change equation version of this, but if you're more familiar with the stochastic differential equation representation, you'll realize that this is just basically a squared Bessel process accelerated. So a really particular case of a CIR model. Then, because you chose delta to belong to 0, 1, 0 is regular and instantaneous for your limiting process Z, for your squared Bessel process Z. And then you can prove convergence of the Galton-Watson process with immigration scaled and your scaled local time towards the limiting process Z plus a multiple of its local time at 0. Furthermore, it is very well known, a very well-known fact first proved by Molchanov and Ostrovsky, that the local time at 0 of a squared Bessel process is the inverse of a stable subordinator. So here, what we have is that the inverse local time is a stable subordinator of index 1 minus delta. And the funny thing is we don't need this result of Molchanov and of Ostrovsky. We can just deduce it from computations that arise when trying to apply our main theorem. So in terms of the conjecture here that I just stated, the reproduction mechanism would just be the Laplace exponent of scaled Brownian motion, and the immigration mechanism would be the Laplace exponent of a trivial subordinator of a drift. So this is the simplest version of the conjecture that we can prove, and we should at least be able to extend it to when this is the Laplace exponent of a spectrally positive alpha stable Levy process of index between 1 and 2, and when this is the Laplace exponent of an alpha minus 1 stable subordinator, because in that case, this limiting process Z will be self-similar. And we think that that should be the next step we should make. Well, with this, I'll stop and just thank you for your attention.
Very much. Questions? Yeah.
So one of the applications you have, I mean, for this application, for instance, you have a explicit formula for the inverse of your inverse of time. I know it's stable, but in previous cases, you know,
sometimes you can know them, right? In general, no. You only have your Levy-Kinshin representation, and the funny thing is you don't need it. You don't need to know it in order to use the limit theorem. Yeah. Yes, exactly. So I'm trying to remember if. No, I think even here in the paper by Chaumont and Donny, I mean, there's a very complicated expression for the Laplace exponent. It's not even worthwhile to look at it. It's not explicit enough, except in special cases.
Any more? I think I've got one, which is you imply that you could do this not just for local time at 0, but for. So here's your opportunity to explain how it generalizes.
Great. So thanks for the opportunity. Yes. Basically, what we can do is to use our main theorem at any finite number of levels. Right? Why? Because our limit theorem features convergence and probability. So we can just put any finite number of levels. So we can basically have a certain type of finite dimensional convergence of the local time field, if we can apply the theorem at all levels. The only remaining part to prove a limit theorem for the field itself would be to prove some tightness results, right? Which are usually very technical and difficult. But here, the funny thing is you won't need tightness in both variables, right? Because for one of the variables, for the time variable, you already have the tightness thanks to the limit theorem. So we do believe that this is a good first step towards proving local time field convergence, but we decided to leave the tightness analysis for a later project.
Okay, thank you. We're still, can I follow that up? So this is, you're essentially taking, if I've got this right, it's always discrete time and then convergence. So can you do I mean, you know, continuous Markov chain type version?
We haven't actually thought about that. I would say yes, but I'm not very confident until I see the details.
Okay.
I would say yes.
Thank you. Last chance. If not, we've actually got, thanks to our speaker's promptness, we actually have 5 minutes. So our next speaker can set up, and If anybody wants a 2-minute break, that's fine. Thank you very much. Thank you.
Thank you.